All right, moving on. We have three different transitions. So if you are looking for a transition from any number all the way to n equals 1 for hydrogen, given a series of spectral lines in the UV region, that's called the Lyman series. Transitions down to n equals 2, this is the Balmer series, and transitions down to n equals 3 give a series of spectral lines in the infrared region called the Paschen series. So we have UV all the way down to 1. We have visible. This is going to be the one we're dealing with here. Right? Transitioning down to n equals 2 to give visible. This is our Balmer series. And then the Paschen series is the infrared. You see how there's multiple lines? And as we're looking at the different energy transitions, so this one goes 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1. So these are the possible transitions that are happening. I have seen questions that say, draw in the possible transitions that would happen given a visible spectra. So you have to know it's going to be 5 to 2, 4 to 2, 3 to 2. So just remember you can go up as high as you can go without getting to 0, and then dropping back down to n equals 2, or dropping all the way down n equals 1, or dropping all the way down n equals 3. If there was a transition between 5 to 4, then we would have only these two lines, from 6 to 4 and 5 to 4. And then if we wanted to transition to 5, then it would be 6 to 5. Recap here, the emission and absorption spectra of hydrogen is predicted to contain a line spectra at very specific wavelengths, which is always verified by experiment. So which is the emission spectrum and which is the absorption spectrum? You have to know this. You have to be able to identify. If it's got a red line, it's the emission spectrum. It's just like when we use the spectroscopes and we looked at the different elements in class. That's what we saw. Blackness and then some color. The absorption spectra is a continuous spectra with some lines missing. Some certain colors are missing. Because the higher states are closer to one another, the wavelengths of the photons emitted tend to be close to. This is called crowding of wavelengths at low wavelength part of the spectrum. So you see how that's happening. All right, so a quick review. E equals HF. E is energy, H, Planck's constant, and F is the frequency. Frequency is measured in hertz. A hertz, remember what a frequency is. Frequency is the inverse of a period. So the inverse of the time it takes for one complete cycle of a wave to come by. So frequency is an inverse second, and an inverse second is equal to a hertz. So if we take H, which the unit here is a joule times a second, multiply that by an inverse second, our seconds will cancel out, and what we're left with is energy in joules. But we were looking at energy level diagrams in the diagram, Bohr's model diagram, in electron volts. So what is an electron volt? Whoops, wrong button. An electron volt is the energy, potential energy that an electron gains as it travels through a potential difference of 1 volt. So an electron volt is the potential energy that an electron gains when it travels through a potential difference of 1 volt. In practical terms, we would say that 1 joule of, that's the harder conversion. 1 electron volt of energy equals 1.6 times 10 to the negative 19 joules of potential energy that are needed to go through a potential difference of 1 volt. Remember that a volt is the work done per charge. So if we take a charge and we put it through a voltage of 1 volt, the gained potential energy equals the 1.6 times 10 to the negative 19 joules. All right, so remember this conversion. Have this deep in your brain because it comes up very often. All right, so a quick recap of the electron volts. Again, it's the potential energy gained when an electron travels through a potential difference of 1 volt. Electron volt. What else? And just that 1 joule equals 1.6 times 10 to the negative 19. Come on. That's not right. 1 electron volt times that. How are you going to know if you mixed it up or not? Well, are you dealing with a big quantity of energy as you're jumping energy shells, or a really small amount of energy? By now in this class, you kind of have a feel for what a joule is. So is it going to be more than a joule, or is it going to be less than a joule? 1 electron volt is going to be much less than a joule. Notice that times 10 to the negative 19, that means there's 18 zeros in front of all of this. So it's much less than a full joule. And it takes a whole bunch of them to equal 1 joule. So don't let me mess you up there. On to the equation sheet. This is what it looks like on the equation sheet at the time of this recording. If it's changed, then that's somebody else's problem. So we have E equals HF, lambda equals HC over E, solved for lambda here, but it's the same equation as this E. And then we have Planck's constant, H, 6.63 times 10 to the negative 34 joules per second. This is on your constants part of the data booklet. Try this example. Calculate the energy carried by 1 photon of microwaves wavelength 10 centimeters. Like you see in a cell phone, in joules and in electron volts. Go ahead and pause it and try it out for yourself. All right, here we go with the solution. First thing that I notice is centimeters, so that's no good. That's no good. We need to have this in meters, of course. And 10 centimeters equals 0.1 meter there, so good. Wavelength, I know that's going to be my lambda. Okay, so my lambda equals 0.1 meters. I'm looking at energy of a photon. These two words together instantly bring up E equals HF, because this is the energy of a photon. We're not given frequency, though. But we are given wavelength, and we know it's a microwave, and a microwave is what kind of wave? A electromagnetic wave, electromagnetic radiation, which all of that travels at 3 times 10 to the 8th meters per second. So I'll use the second form of the equation, E equals HC over lambda. Then substitute and solve. And we get 1.99 times 10 to the negative 24 joules. Now converting that to electron volt, using my conversion factor here, I do my dimensional analysis here, and I get 1.24 times 10 to the negative 5th electron volt.